The advances on the observational front are truly spectacular, less so on the theoretical front. And so I will be describing a very unorthodox approach to theory brought about by dissatisfaction with where the field is, the confusing state of so-called fundamental physics. So a few years ago, dissatisfied by this, I and my colleague, Latham Boyle, decided to attempt to reboot the connection between cosmology and fundamental physics by being much more demanding. And our first basic principle was not to introduce any new particles where there was no evidence for them, and instead to think a bit harder. So I'm going to explain this. It's this recent work with 3 very good students at Edinburgh, and Latham, who has joined me in Edinburgh. So our motivation is that lambda CDM provides an amazingly economical fit to the large-scale universe. Just 5 parameters, 3 for the energy and 2 for the perturbations. Very many potentially present parameters have turned out to be consistent with 0 so far. No tensor perturbations, no isocurvature, no space curvature, no non-Gaussianity. The universe turned out to be much simpler than was expected. It's an extremely predictive theory, lambda CDM, as many people have emphasized. I was very fortunate in the early 90s to calculate the polarization of the CMB for the first time, and or rather the temperature polarization cross-correlation. And there's the curve, and there are in principle no free parameters in that curve. You fit the cosmology to the lower curve, the temperature, and that's just a prediction. So it's amazing. There are very few fields in science where such precision is possible. It's a similar story in particle physics. The LHC has so far seen no deviations from the standard model. This is a huge shock and disappointment to most particle theorists, but it's the same story. The universe has turned out to be simpler than expected on very small and very large scales. And so perhaps our theories have just become too complicated and contrived, and maybe only a very minimal extension of the standard model in GR is required. So let's start with inflation. Now, inflation, as you know, has 10,000 incarnations with arbitrary numbers of parameters, but there is a minimal version. And I think the motivation for studying it is very laudable and very similar to ours, which is the following. Take the standard model Higgs with a quartic potential, which is the most general renormalizable potential. And then instead of just coupling it to Einstein gravity, add this non-minimal coupling. Okay, so it seems like a modest thing to do. But the slightly strange thing is that you have to take this parameter to be very large. And then you do a sort of card trick, which is a change of variables. And you say, oh no, I really should be in Einstein frame, and redefine the metric and the scalar field to remove this and make this canonical. And you get a new scalar field, which happens to have an extremely flat, exponentially flat potential. So this is not a fundamental principle. It's a sort of game of changes of variables. Nevertheless, it's an interesting thing to do. And moreover, so you get this potential with a flat plateau that looks good for inflation. A sort of complication of the story, which is really interesting in its own right, is that the standard model of particle physics is very close to the parameters where the vacuum we live in, which is over here, may be metastable. In other words, there may be a lower energy vacuum at larger Higgs VEV. And so this has been very fascinating. The LHC has been measuring all the relevant parameters more and more precisely. The situation is still not completely clear whether we live in a metastable vacuum. The odds are it is stable, but you get into this discussion of potentials like this. But for the purpose of inflation, they're really only using this part of the potential. The tricky point about this theory and its Achilles heel is that because you're sort of mixing up a renormalizable theory, which is very tightly defined and very principled, with a non-renormalizable one, which is gravity, and you're doing so in this rather strong way, the best you can argue is that what you get out of this is an effective field theory, which has a huge amount of freedom in its predictions. You can add all kinds of extra operators. So to some extent, this is a game of choice. Nevertheless, if you include only a minimal set of operators and assume 60 e-folds of inflation, then you get the following. You fit the amplitude with this parameter, rather large, and you predict the spectral index and the gravitational wave background from inflation, which are a great target for CMB-S4. And so to see if this theory is, or this model is correct, we just have to wait a little while. Here are the forecasts for S4. They hope to measure R to less than 0.001, and here is Higgs inflation. So in my view, this is the leading remaining theory. By the way, all the monomial theories of inflation are now ruled out anyway. This is the sort of most plausible, if you like, model that's left, and maybe ruled out soon. A more general analysis of the effective field theory, which puts in other operators, gives a wider range of predictions, but those two can all be ruled out by NS. So let's look beyond inflation. Let's imagine that S4 does rule out Higgs inflation. Then I think the whole story becomes rather contrived and implausible. And so is there anything better? So I'm going to tell you our story. So it started from the point of view that CPT is the most basic known symmetry in physics. That is charge conjugation, parity, and time reversal. When you reverse the arrow of time, you change particles into antiparticles. And when you invert space into parity, combine these operations, all the laws we know are invariant under that. String theory is invariant under that. In fact, we believe that any theory which incorporates special relativity and quantum mechanics has to be invariant under CPT. So let's make a very radical hypothesis that despite appearances, the universe does not violate CPT. Okay. There's more matter than antimatter in the universe. The universe has an arrow of time. So it looks like it violates CPT. But our hypothesis is actually maybe it doesn't. The way in which it doesn't have to is if you take the Einstein equations seriously, the Friedman equation in cosmology, and you consider what's called a maximal analytic extension. So I solve the equations for cosmology back through the radiation epoch. And all cosmologists will know that the scale factor goes linearly in time with conformal time, near t equals 0. So you can extrapolate that solution through. That's the analytic extension. And when you do that, you find a mirror universe on the other side, which is the image of ours. And there's now a time reversal symmetry to the extended cosmology. So you can define CPT, and if you do so, you'll find for every particle on this side, there'll be an antiparticle on that side. Matter here has antimatter there. So it's extremely radical, but the reason this is possible is actually very fundamental. It's due to local scale symmetry. That radiation, as you know, Maxwell fields or even Dirac fields, are the same no matter if you scale the wavelengths up or down. The equation is invariant. And that symmetry is even local. You can rescale space locally, and the equations are invariant. And the consequence of this is the stress tensor for radiation, Maxwell or Dirac, is traceless. Ricci scalar is 0, and that's the consequence, is that the scale factor of the universe goes to 0. It's what's called a conformal singularity. The Big Bang singularity is only conformal. It's only in the size. And the radiation doesn't even detect the size. So as far as the stuff in the universe goes, it's not aware that the universe has shrunk to 0. So what we're doing with this picture is imposing CPT-symmetric boundary conditions at the Big Bang by insisting that the pre-Bang universe is the same as the post-Bang universe. And we're discovering that's completely consistent with the Einstein equations. You can think of this as imposing a symmetric boundary condition via the method of images. This is the image universe. And so the Big Bang is actually a mirror. And rather than solving the equations in the presence of a mirror, we're doubling the space, throwing the mirror away, and solving the equations. So if we look at the equations for cosmology, here's the metric in conformal time and co-moving space coordinates. And this is the Friedmann equation. And amazingly, it wasn't noticed until our work that the maximal analytic solution to this equation, it's a very beautiful equation, just a quartic oscillator. Maximal analytic equation is two-sided. There are two sides to the Big Bang. And furthermore, it's periodic in imaginary time. So most cosmologists wouldn't think of solving this in imaginary time, but this is exactly what people did in the theory of black holes. They realized that all black holes that we know are actually periodic in imaginary time. And this was crucial. This gave an explanation, which Malcolm Perry, who's in the audience, among others, is responsible for, that black holes have a temperature. So, by the way, you might think that's just a fluke of cosmological solutions. It's not. If you consider inhomogeneous cosmology nonlinearly, actually in a gradient expansion, half of the solutions are time reversal symmetric. And this conformal 3 geometry, where I've factored out the scale factor, provides complete Cauchy data for the future or the past. So basically, you can impose this time symmetry on inhomogeneous cosmology, providing you have domination of radiation, traceless stress tensor at the Big Bang. This is similar to black holes. This, for example, is a Kerr black hole. And as we all learn, all black holes have a two-sided exterior. And the two-sided Big Bang is quite parallel to the two-sided exterior of black holes. There's a universe with time going one way on one side and the other way on the other side. And in very recent work, we've generalized the CPT picture to black holes. But I won't talk about that. Black hole thermodynamics. So what was the idea? Time evolution in quantum mechanics becomes the Boltzmann factor in statistical mechanics if you take the time to be minus I beta, where beta is 1 over the temperature. And this was the basic trick used to infer the Hawking temperature. It's just the imaginary time period of the black hole space-time and the gravitational entropy, which is simply the action for gravity calculated over one imaginary time period. So this is a very formal trick. People are still very puzzled about what it means for black holes, and there's a huge debate in the literature, etc. What we realized recently is we can apply exactly the same trick to cosmology, and it works unambiguously. So the gravitational entropy can be calculated for realistic cosmologies with these CPT-symmetric boundary conditions, including inhomogeneities. And the amazing thing is this provides a measure. This tells you how many states there are corresponding to a given cosmological spacetime. The measure is the one thing that's been lacking in cosmology. Inflation has never come with a measure. It's always been a matter of sort of intuition, if you like, what spacetimes were probable or improbable. And the measure problem got even worse with the anthropic principle, where everything rests on this prior measure, which nobody knows. Well, here's a measure. It just happens that this measure is greatest for homogeneous, isotropic, and spatially flat universes. And it's also greatest when the cosmological constant is small and positive. Okay, these follow unambiguously from the mathematics. So when you realize this, you say, wait a second, if most universes look like this one, we don't need any mechanism to make the universe big, flat, and smooth. It's just the most probable universe, just as the air in this room is homogeneous and isotropic because of statistical mechanics. The same might apply to the universe. So if this picture is true, there's no need for inflation. So let's talk about dark matter. Here is the standard model, incredibly successful, precise theory, surprisingly successful, continues to fit all the data at LHC. How could we possibly explain the dark matter based on what we know of particle physics? So the simplest answer is the following. 3 generations. Simplest answer is the following. You may not have noticed that. There's been one change in going between these two slides, which is that L disappeared. Okay? This is the standard model as fits everything at LHC. This is the standard model with right-handed neutrinos. It's the minimal extension you can make. It was postulated in the 70s in order to explain neutrino oscillations. It's very plausible that they're very heavy right-handed neutrinos which mix with the left-handed ones. When you remove the L, obviously the model becomes more symmetrical. For every left particle, there's a right particle. So it's a rather natural extension. And it turns out this is enough to explain the dark matter. By the way, for future reference, you can count the number of fermions in each family. Each of these guys comes in left and right, so there's 2. 2 times 2 is 4. You get 4 here, but there are 3 colors under SU3, so 4 times 3 is 12. 16 fermions per generation, so 48 in total. That's the standard model. And I'm telling you this because I'm going to explain the 48. So a stable right-handed neutrino is the dark matter. This is the most obvious candidate, but was overlooked for decades. For the simple reason that nobody knew how to calculate its abundance. Because if it's stable, it doesn't actually couple to any other particle in the standard model. It only couples to gravity. But we found a mechanism whereby where it's created, and that explains its abundance. So it turns out the right-handed neutrino field equation is regular at the bang, namely has a unique solution across t equals 0. We select the CPT-symmetric vacuum state, and this allows us to predict the number of right-handed neutrinos in the out state. So it's a very simple calculation in time-dependent cosmological background, and you uniquely predict how many right-handed neutrinos there are. If one of them is stable, its density matches omega in dark matter if its mass is 5 times 10 to the 8 GeV. So that could be the dark matter. Now, how does it become stable? Well, you take the standard model with right-handed neutrinos to explain neutrino mixing, and you impose a symmetry to make one of the right-handed neutrinos stable. You just literally turn off its coupling to the Higgs boson. So I want this guy to be stable, so I just switch that coupling off. Well, if I do that, that's the same coupling, so this coupling goes off. And that means that the left-handed neutrino no longer mixes with right, and so it doesn't get a mass. So the prediction of this is that one left-handed neutrino is precisely massless. Okay, and that's about to be tested using these wonderful galaxy surveys. So here are the 2 measured mass differences between neutrinos. We predict the lightest one is massless, so then we predict the sum of the masses to be the minimum value, 0.06 eV. And we've seen this graph before in this workshop, that this curve, as Carlos was emphasizing, looks like it's favoring negative total mass, which is a bit crazy. But as this curve sharpens up, if it sharpens up around 0.06, this will be very strong evidence in favor of the right-handed neutrino being the dark matter. And maybe that's the problem solved. There are other predictions, by the way, of that picture. So I want to end by talking about perturbations. Inflation's most amazing success was in predicting a spectrum of scale invariant density perturbations, which could then form galaxies. How do you generate the perturbations if you don't have inflation? So it turns out there's a simple answer, which again has been overlooked for a long time. To find the answer, you have to go back to the roots of quantum field theory in curved spacetime. So here's a picture of quantum fields, in this case QCD, in the vacuum. As you know, they have violent zero-point fluctuations. And if you just go ahead and calculate the energy and pressure in the vacuum, it's infinite. Okay. So the vacuum is full of energy and pressure. You can normalize it away, but throwing away this potentially infinite source for gravity should make you very queasy. Okay, and this problem has been discussed for a very long time. Likewise, these divergences in quantum fields, this divergent energy at short distances, spoils the symmetry of the Maxwell and Dirac fields. The local scale symmetry gets spoiled by these divergences. And since we needed this symmetry to understand the singularity, the Big Bang singularity, we have to fix this. So here's the stress tensor in the vacuum, and you get two anomaly coefficients. These cannot be renormalized away. Standard model fields all contribute positively to these coefficients, so no cancellation is possible. You've got to add something which is not a standard model type field. So we discovered what that was. It's a four-derivative field called a dimension zero field. And so as I'll show you, this can be used to cancel all those divergences. It also has a scale invariant spectrum, just like we need to explain the perturbations in the sky. So in view of time, I won't dwell on this, but basically the vacuum energy and these anomalies are just sums of integers with funny coefficients. And it turns out that if there are 3 generations, 48 fermions, those all cancel, provided there are 12 gauge fields as in the standard model. So for the standard model gauge group, cancellation of all these things demands 48 fermions. Under some simple but important technical assumptions, we then calculated the cosmological perturbations and found that this conformal symmetry demands these perturbations take this form. So these numbers are all calculated, I think, honestly and carefully, but and encourage everyone to check our calculations. But I emphasize there are important assumptions, namely this conformal symmetry. The power spectrum of primordial fluctuations is predicted from the standard model and these dimension zero fields alone. And the famous tilt of minus 0.04 turns out to be 7 times the strong coupling constant over pi. Amazingly, this is in agreement with Planck. And furthermore, the amplitude comes out right without any fiddling, within a factor of 2. It's very, very surprising. So potentially we have a much more predictive theory than lambda CDM, connecting the very smallest to largest observable scales in the universe. So to summarize, there may be a thermodynamic explanation for the large-scale geometry. There may be a minimal explanation for the dark matter, a new way to cancel a standard model's vacuum energy, a new prediction of density perturbations without inflation, explanation for 3 generations of fermions. I haven't talked about the baryon asymmetry. This actually follows very easily from the picture above through a mechanism called leptogenesis. And the CPT symmetry has suggested we take another look at black holes to try and figure out what's really going on inside them. And that's, of course, incredibly exciting in view of the fact we can see them. So this is only the beginning. Much remains to be done. Happy birthday to the IOA, and thank you for listening.